Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll learn how to combine sound-absorbing materials with sound barriers to create optimal material combinations to contain sound.
So let's get started. We know that absorbing materials are good to pass sound or dissipate it depending on the tortuosity of the material itself at small scale, while barriers are used to stop sound. So a brick wall is a great barrier, while fiberglass batting, used for thermal insulation, is a great acoustic absorber. But when we look at common products, vehicles, or partitions, we see the combined use of absorbing and barrier materials. For instance, in how building walls are constructed, in how aircraft frames are designed, and in the use of recording studios, high absorbers in the room, and a wall that's extremely rigid to stop the sound from radiating outside. So how are materials used in combination like this? Tabulated transmission loss values help us to understand the capability for any of these materials to be a barrier. So take, for instance, the transmission loss table that's reported here. This can be measured experimentally, as we've learned before. In octave bands, fiberglass has very low transmission loss, excepting at high frequencies where dissipation alone provides some minor TL value. Yet concrete that's unpainted leads to extremely high transmission loss values, especially at high frequencies. Interestingly, painted concrete has less TL, excepting at very low frequencies. This is because the paint serves as an impedance matching layer, which we've found so far leads to enhanced transmission of sound. So although concrete when painted may be more aesthetically pleasing, it's actually worse as a barrier. Drywall with studs and insulation inside provides fairly good transmission loss across the board. And glass panes, likewise, with insulation in between two separate glass panes, provides transmission loss values approaching 30 decibels. And doors with seals are much better than their counterparts without seals. A good door with a drop seal could also provide 30 decibels of transmission loss, while that same door, if opened by just 25%, leads to transmission loss values that are uniformly around 12 decibels, indicating the significance of that opening to pass sound. Now, if we compare absorbing materials and barrier materials, we find trends. So take, for instance, fiberglass. It's 4-inch thick, has almost no transmission loss, but extraordinary absorption coefficient across the board from 125 Hz to 4 kHz. Now, concrete that's unpainted is a great barrier. It's also a fairly good absorber at mid levels. But when painted, both the transmission loss values reduce as well as the absorption coefficients, due to the fact that for transmission, the paint serves as a impedance matching layer, while the paint in terms of absorption results in a barrier-like coating over the pores of the concrete. Now for drywall on studs with insulation, it's likewise a fairly good barrier, and a moderate absorber at low frequencies, due to trapping of sound in between the drywall and studs, with insulation inside. But at high frequencies, the absorption coefficient of the wall is fairly small, since on the surface, the drywall that faces the incident sound is quite reflective. The insulated glass window pane is a great barrier, and it's a moderate absorber at low frequencies, once again due to the gap where sound is trapped in between the two panes, and reflections create a slightly enhanced absorption coefficient at low frequencies. So what we see then, altogether, is that to limit noise in a given room, we want to have our room designed with a hard barrier on the outside. And soft treatments would then be placed inside the room. For instance, hangings on the wall, carpet, bedding, furniture, and so on. This helps to limit the peak sound levels and reduce the T60 value for the room. But if we're interested to stop the transmission of sound between rooms, we want, first and foremost, two barriers on both faces of an absorbing material, like we see in the photograph on the right. Drywall, insulation, drywall. This helps first to block the sound from going into the insulation, but if it does get into the insulation, it's going to be reflected by the next barrier layer of drywall. But if some of that still escapes, thankfully it's partly dissipated in the insulation, yet still gets back to the receiving area. This practice is not only used for building construction design, it's also used to tailor sound in aircraft, vehicles, and for a wide variety of products where noise is otherwise a concern without treatment. So let's summarize what we've learned. Absorbing materials are oftentimes poor to stop sound, while barrier materials are oftentimes poor to absorb sound. But a good practice to achieve noise control will combine the use of a barrier material and an absorbing material in tandem. This practice is relevant whether we're talking about the design of rooms, consumer products, vehicles, and much more.
That's it for this video. In the next video, we'll learn how sound transmission characteristics change when the partition layer is flexible.